Okay, hi everyone. Um, this is the start of our sharing session for our M53 CTF team. So we will do this once every 2 weeks at this time, every Tuesday 9 p.m. We'll share more about how to get the details later. So today I will share about file parsing bugs, which is quite common in many different software. So we will look at the bug patterns, and then we'll see some real life examples of how this bug is, uh, how it happens in different types of software and how it can be exploited. And also we'll discuss a bit about how people try to find these kind of bugs. Okay, so first we start off by looking at this from a software developer's perspective. We see the developers, how they write code or why they write code for file parsing. So the use case is quite simple. Is to load or store data. For example, we are very familiar with image files, videos, or PDF files, or Word file, a lot of different kind of files, and also fonts. Fonts actually is quite complicated, and in the past there were also a lot of bugs in the font parsers, but these days a lot of them are fixed already. And then other than this, maybe some programs like Photoshop or the AutoCAD, they like to save their project state because there are many complicated information inside. So maybe the parsing for these files may have bugs also. So we'll look at that later. So here are some example of file formats. So just now I mentioned for media, there's a lot. There's MP3, then for audio, there's MP3, AAC, and maybe 10, 20 more other audio formats. And then for images, also got all this and so on. And then we have, for documents, we have PDF, the Microsoft Word, XML, and then for font, we have True Type font, Open Type font, and this one is an old type, legacy one that I'll share a bit about later. And then some custom ones, like I mentioned just now, have this Autodesk, they have this AutoCAD, which is for their 3D modeling. And then this DCOM, if you search online, you also see that there are some parsing bugs for some DCOM parser. It is for, I think for hospital, they use it for X-ray. And then also, for example, Adobe Illustrator, they will try to load the project files from other drawing software like Corel Draw or this one. So you may expect there may also be bugs because the file format is the standard comes out from Corel Draw, but Adobe they have to write the code to parse this file format. Then you'll see maybe they cannot 100% follow the specification. Okay, so here we also should know that for file parsing, there are a lot of standards. For example, PNG is by this Web3 consortium, then MP4 is by the ISO, and then TrueType font, it is developed by Apple and Microsoft, or PDF by Adobe. So the standard is the people, the organization that determines or set the standard for the file format, because uh, there must be one person that decide what is the actual file format, right? If otherwise, different people can say different things. So we all follow one standard. And then every software that needs to parse these files, they will follow they will go and read the specification in these standards, and then they go and implement accordingly. So now we talk about implementation. Many of them have open source implementations. For example, PDF, there's this PDF film by Google. And then also this one, PDF box is Java, it's written in Java, or this PDF parser written in Python. So it depends on the programming language. People can use the different libraries. And then for images or videos, there's all this libtiff, libpng, libjpeg, libwebp. We can all use this open source. Then for font, there are, I think, less open source, but the very popular one is Harfbus. So now the question is, if you don't want to use these ones, maybe you think it's too big or they don't support some things you like, then is it okay to use a random library that you found on GitHub or write your own one? So we'll think about this. So the few ones that I mentioned just now, they are popular and you see they are written by well-known organizations. So there's a lot of testing that has already been done for correctness and security. And also a lot of fuzzing always running every day in their servers. But maybe it doesn't support your favorite programming language because you see, this one are all written in C. Then maybe you want to write for Java or Python. I'm not sure if they support those languages. Then maybe you want to consider using some random open source library. For example, you see, you go to GitHub, then you try to find JPEG parser. Then you see maybe got 12 stars on GitHub. And then you have to think about, does it work? Or if it works, are you sure it's secure? Maybe, who knows? Maybe got some bug inside. Or even worse is, do you even trust the person that made the library? Because maybe got some backdoor inside, you will not know. So be very careful when you use random open source libraries in your commercial your projects. But even worse is you make your own parser. If at first you think about it, there's none of these problems. You write yourself, you can make it work. You can say that you are very hardworking, then you make all the parsing work correctly, or it is secure also because you can check everything yourself. But probably a bad idea because later we will see that a lot of big companies, they write their own parser and there are problems because the problem is that file parsing is a very complicated and is very prone to errors. So later when we look at the bug patterns, we will see why or in what way there will be bugs. And then even quite bugs that look quite hard to exploit may also be exploitable. Okay, so now we skip the intro already. Now let's look at the bugs. So first we look at this simple format. Let's say the file only have one header, which is the length 4 bytes. Just put the length like this in, let's say in little endian. So for example, we set the length of this file to be 8 bytes. And then we have a data field, which is all the data inside, depending on the length. So all these look quite simple. Then maybe someone that wants to write a parser will write something like this. So maybe you got a file that takes in the contents, which is all of this, and then you run this parse function that takes this one. This one is the destination to write the file whatever you parse inside, and then this one is the contents here. So you get the first 4 bytes, which is the length of the data. So this one, if you are not familiar with C, I just explain a bit. So at first, source is a char pointer, so it points to the first character only. But you cast it to a int pointer, now it points to, is consider this block as an integer, so 4 bytes. Then the reference, so you can get the length. And then you advance this source pointer forward by 4 bytes so that you can start pointing at the data. And then you run a copy. So you see the length is this one, and then the source is this part. So memcopy will take 8 bytes from source and copy into the destination, which is be given to be this one. So everything looks quite normal. So anyone here can suggest any possible problems with this? Okay, now I will now give a hint. So you consider now, what if the length is 100? And then, but your file is still just this. Your length you set to 100, but the file is just this. Then when you call mem copy, you copy 100 bytes from here. So something is being copied that is not part of the file. So this one, there's a out of bounds read. So if the file contents, this one is on the stack. If this contents is on the stack, then you can read other local variables. Or if they're on the heap, then you can read other things that are on the heap. So if you have a stack out of bounds read, let's look at this example. Let's say you have this read file contents, just some functions to read this file into here, so 512 bytes, and then you read again a secret file into here. So you remember just now this handle file function is vulnerable to out of bounds read. So if you can set this length to be very big, like 600, then it will read past this 512 and also read this password. And then it will save it into here. And then depending on what is being done to this data, maybe you can leak some sensitive information. So maybe you can leak sensitive information like the secrets that are written into the local variables. But even nicer is you can read the stack canary also, because this one will be useful if you have a buffer overflow, stack buffer overflow later. Or you can leak some pointers. So in this example, there are no pointers, but maybe you can read past the stack return address, then below there are some pointers. Then they can be useful for bypassing ASLR also. So this is there is some impact for this to this out of bounds read. Similarly, we also look at a little bit different example. So if your values are not on the stack, but they are allocated with malloc instead, so they'll be on the heap. Then you can read the values of other allocations. So for example, file contents and password, they're on the heap. So when you trigger the out of bounds with handle file, you can still also read the contents of password if you give a very big length. So just now, as we see, out of bounds read, it doesn't look that bad because you cannot get RC right because you don't corrupt anything on the stack. So we will look more into the exploitability of everything later. So now, do you think we can do more than out of bounds read? Any ideas? Yeah, you can do buffer overflow with some custom data. Let's see. So now, just now, we set the length to be 100. Then it is still within the bounds of this. It's just that you can read past the file contents itself to whatever is allocated after the file contents over here. But now, if we set the length to be very big, then your destination is only allocated this very smaller size. Then we can do out of bounds right, because now our mem copy is copying 512 bytes into only a buffer that's only 256 bytes. Okay, so it's quite similar. If you are familiar with binary exploitation, then this should be quite standard. But if not, then let me go through a bit. So over here, our pass file function may overflow this one. So it writes 512 bytes into here. Here only got 256, so it will overwrite whatever comes after in the stack. And that may be other data. For example, if we have loaded some password or some other variables that are useful for some logic, then you can overwrite. But over here is already very nice. You can already overwrite the stack canary and the safe return address. So actually, stack canary is to protect the program from buffer overflow. So you have to override the stack canary, and then you override the safe return address to either jump to somewhere or do return-oriented programming. Then on the heap, it is a bit similar. You cannot override the return address, but there may be also other sensitive data on the heap that you can use to affect some logic. So this one, we'll look at an example in a Windows kernel exploit later. But just a brief idea is you can override some um, pointers or some metadata on the heap because there are many different objects. Maybe there are many different objects on the heap. So we'll look at a more specific example later. This one just give a brief idea. So to summarize, with this out of bounds, right, you might be able to get code execution because you can do return-oriented programming or you can override some function pointer on the heap. And we will look more into some examples later. Okay, to summarize this one, because the example is quite lean, there will not be a file format that is so simple. But some takeaways is the problem comes from the size field is too small. The size field is larger than the file content. So over here, just now we specify that this one we give it 100, but actually the file content is smaller than 100. Or this one, the allocated buffer is too small. We tell it that the file has 512 bytes, but we only have space to store 256. So let's look at how we can prevent this kind of bugs. So if you are a developer, then this is important to know. So first is you want to make sure that the value of the size field is larger than the actual size of the file contents. So this one, the size field that you read from the file header, you must make sure that the file contents, for example, over here, we say the file size is the size of the file, the size of its contents, and then we make sure that the length is greater than the remaining contents after you remove the header, because you want to skip the header already. And then you also want to make sure that the buffer to store the pass data, the destination, is nicer if you can dynamically allocate, because if you set a allocate on the stack like this, is a hard-coded size, then maybe the file contents is bigger than this, and you cannot know, it's very hard to know. So it'll be nice if you can just allocate on the heap with a dynamic size. But if you cannot do that, it's also okay. Then you just make sure that in here, you make sure that you don't copy more than this size. Okay, so what I just say is what I written here. You want to avoid allocating buffer of hard-coded size because you may not know if you want to copy more than that. But if you actually do it, you must make sure that everywhere that does the copying, it copies less than the hard-coded size. So if here 256, you must make sure that here you copy less than 256. Okay, now we look at a format that is a bit more complex. So let's say we have a grayscale image. So grayscale image is the image is black and white. So you see, I got question. But I think you all maybe answer the question already. Okay, maybe I wrote something wrong over there. Okay, we continue with this one. So let's say you have a grayscale image file format that's like this. You got 2 bytes to say the number of columns, but like this, and then 2 bytes for the number of rows. And then after that, it just counts all the pixels, which is number of columns and number of rows. You multiply them together to get how many pixels is stored inside. So let's look at a sample implementation for this. So for example, you can load these 2 fields, and then you multiply those fields together to get the number of pixels. But this time we do things correctly. We check if the number of pixels is greater than the file size. So this one is to make sure that when you say that the number of pixel is something, it doesn't read more than what we actually have in the file. So if the number of pixel is more than the file size, then you just abort. Don't copy because it is a wrong value already. Okay, after that, you use malloc to allocate the number of pixels, a buffer of this size, so that you can copy all the pixel inside and do the processing. Okay, then we advance the pointer to +4, so until here. And then let's say in this implementation, we want to go through row by row. So we do a for loop over the number of rows, and then we copy the contents, but just number of columns. So we copy one column, and then you go to the next iteration of the loop, and then you copy another column, and so on. So this one is just pointer arithmetic to advance the pointer forward. This one you can see by yourself. But now let's see, are there any problems with this? Because as I said, this time we do things correctly. We make sure that the number of pixels that we say here is actually smaller than the file size, and that so that you don't have out of bounds read. And then here, we dynamically allocate the buffer for the pixel, so you don't have out of bounds write. So are there any more problems here? Okay, data type. The idea is there. So what is wrong with the data type, or which data type? Okay, yeah, so it has something to do with the data type. So over here, yes, the over here we say that these two fields, they are 2 bytes. So unsigned short is big enough to store them because unsigned short is 2 bytes. And then this one, n pixels, since we just take 2 bytes times 2 bytes, is it okay to just also store the result in 2 bytes? So because the columns and rows, let's say we give them a very big value like hex FFFF. Then when you multiply them together, it will become a 4-byte value already because the values are so big. But because the number of pixels, the data type that we store it in is just unsigned short. So we only take the last 2 bytes. And then as a result, the number of pixels is just 1 because we store in the unsigned short and we will truncate the top 2 bytes away. And the result is you only allocate 1 byte for this buffer, and there is one big problem already. So now when we move forward, we do mem copy. But remember, number of columns is hex FFFF, and you only allocate 1 byte. Then GG lah. You're gonna overflow this 1 byte buffer with hex FFF bytes. So now let me do a demo. So this one is the code that's in the slides. So I'll open it in GDB, and then we've set a breakpoint before malloc. See this one? We call pause malloc. So we set a breakpoint here. And then also got mem copy. We also set a breakpoint before that. And then we run. Yeah, you see, for malloc, we are only allocating 1 byte for this buffer. And then for mem copy, we are copying FFFF bytes, then get segfault. because there's buffer overflow. Okay, back to here. So to summarize, the problem here is there's integer overflow, or another way to say it is your data type is too small. When you take two 2 byte numbers and multiply them together, you must store them in a 4 byte 4 byte value. So unsigned int instead, or if you have unsigned int and unsigned int, then you should store them in unsigned long long to make sure that there's no truncation of the result because your data type is too small. So you must be very careful of this. And this kind of integer overflow in multiplication is a quite common problem in file parsers because you may accidentally use this that is too small and then allocate a buffer that is too small but still copy very large contents into it. Okay, so these two examples, I just quickly go through so that we all have a brief idea of what file parsing bugs will look like. And now we look at some examples of file parsing bugs in popular software. And then we will discuss a bit how maybe they can be exploited or cannot. So not all will be exploitable actually, and we'll see why. So first, let's take a look at the number of parsing bugs that are out there. So here we look at the ZDI advisories page. This one is for 2024. Then if you type parse, you see got so many already. The software is, for example, AutoCAD. Got a lot in AutoCAD. This one is most likely from fuzzing. So someone just let a fuzzer run in the background, and then the fuzzer finds so many bugs. And then if we go back to 2023, for one whole year, there are even more. Most of them are in Adobe. So you see, actually, I realized many people, they like to fuzz Adobe. You don't even know got this thing that exists. What is Adobe Dimension? I also don't know. All this random software that none of us really know. Like some people, they like to write fuzzer for them and then get a lot of CVEs. I don't think they will get money because I don't think they're exploitable. And I'll talk more about that later. Yeah, then here got Autodesk also somewhere. Okay, anyway, back to this. So first I'll share about this out of bounds read. This is a bug that I found during my internship at Star Labs. So I'll share more about I think it's a quite interesting bug. So I'll share how this bug can happen. But first I give some brief context, some background. So Cortex is Apple's framework. They say it's for laying out text and handling font. So in other words, is take the font and then it calculate the spacing between text or decide how to draw out the font. And the vulnerable library is in this library that is part of the Cortex framework. So this lib font parser. And the bug is in the code that parses this Mac resource font file. So I don't think any of us heard of this font file before because it seems like it's very old from before most people are born, I think. But there are some documentation. If you're interested, you can click on these links in the slides that I shared with you all. Anyway, one nice thing about this kind of legacy file format is there'll be bugs inside because imagine if this parser is written so long ago, maybe at the time those people they haven't learned about all these security problems, all these file parsing bugs. So at the time, the code that they write might be more vulnerable and the vulnerabilities may last until now because at this time no one really even knows about this format already. So there may be also few people that try to find bugs in them. But now let's look into this file format deeper so that you can understand the bug. So the resource file, as the name suggests, it stores multiple resources, and this is the structure. It has a resource header, so it contains just the offset and sizes of these two. Then there's the resource data and resource map. Resource map is, like the name suggests, it's like a map. It stores some information about the resources in the file. So some info like position, offsets, and also some extra information that we will see later. So here, the resource header, you just got the offset to here and this offset to here, and then their length. So nothing too special. And then the resource data also just length and data, just a very simple format like the one I shown just now. So the more interesting part is the resource map, where you can expect there to be some complex parsing that might happen in here. So the few important fields that we'll look at are this one, the num types. So it stores a number of types in here, but in -1. So if you are storing 3 types in this resource map, then it'll be 2. It'll store 2 over here. And then we got the resource type list. So resource type list, it has this number of types inside. And then reference list and resource name list, we look more into that later. But anyway, it's not so important. For the stuff that are related to the vulnerability, I will show them in more detail later. So look at you can quickly look at this code that is used to create a file that follows this format, because too much effort to make the table already. So this one, P16 or P8, there are functions in Cone Tools. So for those who are not familiar with this, let me show an example. So the purpose of these functions, P stands for packing. So it's to pack a number into a string or a byte array. So let's say you P8. So 8 stands for 8 bits. So you pack this 8-bit value into a byte array. And if you have P16, then it will pack it into a byte array as well. So as you can see, it treats it as a little endian number, because hex 42 is B and hex 41 is A. Okay, so the whole point is just you make a byte array out of the number. Okay, we'll look more into the specific parts later. Don't worry. And now we'll look at how Apple, they parse this file format. So first we'll look at this function called checkmap command, which is used to validate the file contents. So validation means like what I shared just now. You make sure that when the file gives a certain size value, you must make sure that the size is actually smaller than the whole file size, so that you don't read more than the file. If you specify a very big size like 100, but the file is just 10 bytes, then you read more out of bounds already. Okay, so there's a bit of things to follow here. So first, it reads this value. So you get a pointer that points to, sorry, you read out this first. This offset is this value. So it says, where is the resource type list? Because over here in between, there may be other things that are variable size, or you can insert more padding. Actually, this one is quite weird. I don't know why they want to do this instead of just have a fixed distance. Anyway, here you specify what is the offset to the type list. And then the num types pointer is stored in the type list. So now you see a bit weird, why over here got this, and inside here also got another num types. So this is actually the bug. They have two values that are stored in different places as part of the specification. So you see that in my example, if you write the number of types to be -1 to be 0, then it will read it out as a little endian number. And then let me go through what this means. It's a IDA, it's a code in IDA to mean convert a little endian number to big endian format. So just flip the bytes. So I'll quickly go through is if on the file the bytes are like this, then when you read it out with an Intel CPU, it considers it as a little endian number. So you'll read out in the opposite direction. So 3412. But the font specification by Apple, because it's from very, very long time ago, and that time they used Big Endian, the Macintosh. So it should actually read out 1234. Then what it does and what IDA calls ROL2 is you rotate the 2-byte value to the left by 8 bits. So like this. So you flip, in other words, you just flip on to make it like this. Okay, so back to the file. So let's say we craft a file. You craft a file that says that the number of types is -1 is 0. Then over here, it will say that num types is greater than 1. Okay, so now we look at the code. You see that over here, it checks if the number of types is less than 0. Then you return. So that makes sense because the number of types should not be a negative number. If not, there's no logic. So you should return with an error. And then over here, after that, it also checks if number of types is equal 0. So it is not less than 0 because here you will have returned already. I think this one is just the IDA give a bit output like this. So if the number of types is 0, then okay, I don't really need to check anything, right? Because there's nothing to check. So you just skip all the validation. Even though your file, you can still put a type list inside. But because the number of types is 0, then okay, just assume that you will never actually use all this inside the file, even though it might be in there. The number of types you say is 0 already. So by setting this value to hex FFFF, over here when it's read out and you +1, there'll be integer overflow, and then num types will be 0. So here you see it is similar to the example just now. Again, the problem with the data type. When you read out 2 bytes and then you try to add values to it, it may overflow. So a good practice is if you read out 2 bytes and you will do some arithmetic operations, it's better for you to set a bigger type here so that there won't be overflow. So for example, over here, it's better to set unsigned int. Okay, anyway, now we see after check map command, after it succeeds, then we'll use get resource pointer command to start copying out the resource info. And you see now, it also reads the number of types from offset 28 because resmap is a unsigned short pointer. So yeah, it's considered as an array of 2-byte values. So 2-byte, 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 2-byte. So if you access the 14th element, then it is from offset 28 in the file. Just to know how this corresponds to the file. And then after that, after going through all the checks again, it will try to copy out the resource name. So over here somewhere, okay, here in the type list, it will have an offset into the reference list. So over here, somewhere here, it will read the reference list, and then it will read the offset, the resource name, starting from the resource name array. So 0, so means that the resource name for this type is here. Okay, I repeat. So you go through the type list. The first type, it says that the reference list is here. The entry in the reference list is here. Then the program will read here, and then it will check the offset to the resource name, and then you will see that the resource name entry is here. And then it will do mem move. Mem move is the same as mem copy. It's just the semantics is a bit, the behavior is a bit different. So it will copy whatever you say the length is into the destination. So I think we all can see the problem here already. It's the same as the example just now. There's a buffer overflow. And why there's a buffer overflow is because check map common is supposed to check that this size is smaller than this or smaller than the file size. What is left in the file. So for example, if this is the end of the file, then you should make sure that when you say 16, 16 is okay. But if you say 24 and this is at the end of the file already, then you read the file out of bounds. So check map common, it actually have some checks over here to make sure that this size doesn't exceed the rest of the file, doesn't exceed the end of the file. But because here we set num types to 0, it skips the rest of the validation. And actually over here, if you think about it, it's okay, right? Because if for check map common, num types is 0, we'll skip the rest of the validation. That is fine because we say that there are no types that you need to process. And then that means that actually we won't reach this vulnerable code because number of types is 0 and you won't reach here. Can anyone see that? Can anyone see any way that maybe we can still reach here? Oh, I see got some question. Oh, yeah, you asked, since num types is unsigned, won't less than 0 always be false? Okay, that might be because I modify some things in the code. I copy out from IDA, then I try to make it pretty. Maybe it's a signed value. My bad. Okay. We go back to the example here. So just now I mentioned a bit about this part where both functions, the same value seems to be stored in two different places. So even the developer also seem like don't know. The developer for check map common reads the offset from the header, the resource map header, and then it tells them where to read the number of types. And then the developer for this just assumes a hard-coded offset in the resource map. So a recap, this one is what I mentioned just now. You read this offset, and then this offset will tell where to read the num types. But for this one, you read a hard-coded offset, read from a hard-coded offset. So you can think about it. How can you make an exploit file to skip this, and then don't skip this, and then get here to do an out of bounds read from the resource name entry. Okay, so this one is leave to you all to think about it. I have a POC on my blog post, but I realized my blog post was not written very nicely, so it might be hard to follow. But let's talk about the impact of this bug. So here we see that mem move. With this mem move, we have a out of bounds read. And when I tried to exploit this, the goal would be to leak some pointers from the heap, because with that you can bypass ASLR or read some sensitive values. But when I did that, there's one thing to take note of, which is this entry, the length is just 8 bytes. So the maximum length you can read, you can do out of bounds read is also just 256 bytes. And when I was working on this, I couldn't find any pointers that are 256 bytes away from the file. So that might be the way that I make this POC. So it might be still possible. We cannot say it's not possible. But anyway, just report the bug. And the Apple, they take very long. I think they take half a year or even longer to fix this. I think because no one want to fix this legacy code. I don't care. Anyway, talk a bit about the exploitation. So the vulnerable function is this one. Okay, so sidetrack is Apple, when they create their function names, it's always something like this. It's very long one. They will say is from what object, then what they do, and they write very long. So if you look at Apple's code, a lot of times their function names got 20, 30 characters on, which I think is a good thing. It's very clear what the function does. But anyway, back to the exploit. To exploit this or to make a POC, you can create an iPhone app. And then in the app, you load this proof of concept font. And then when the app tries to process this font, the app will crash because of the out of bounds read when it reads unmapped memory. Okay, then as for how this bug it can be discovered, if you are interested to find it yourself, first it's found by my teammate through fuzzing. So my teammate just left the fuzzer running, and then the fuzzer found this bug, and then he reported to Apple. Then after that, he told me to reproduce this bug just to learn. Then after that, I only realized that the num types was retrieved in the different ways by the two different functions. And then that means that the way that they try to fix the bug will not be useful, because even though they fix it for check map common, the you can still do this make it skip here, but make it pass this check, because they are actually just checking different values completely. But actually, I also wasn't sure how they fixed the bug, because if not through this, I also don't really know how to exploit the bug. So I'm not very sure what was the POC that was reported by my teammate, because I didn't get to see it. But anyway, here on the company website or on my personal website, I have shared some of my workflow. So, for example, I also tried to use these tiny ints to get coverage. And then the nice thing of coverage is you can sort of know when you make changes to the font file, how much code is being executed. And then you can know if very few code is being executed, that means that maybe the file format is not really following the standard. Then it will fail some check and just stop already. Then the more code that is being executed means that your file covers more code. And then later in IDA, you can use this tool called Lighthouse. You can check it out yourself. Okay. It's a bit late, 9:53 already, but I have a few more examples. So now we'll look at the Adobe Photoshop bug. So as I showed just now, there are many people that reported bugs for Adobe products. Then this one is out of bounds read in the MP4 file parsing. So they say that the CVSS score is 7.8, which means that the confidentiality high, integrity high, and availability high. And then they say can execute arbitrary code. So this one I'm not very sure, because how your out of bounds read can give RC. This one is very weird. I think it's wrong. And integrity, I don't think out of bounds read can affect integrity. So the moral of the story is, I think the CVSS score in GDR website might be wrong. So when you see CVSS score that say high severity, maybe it's fake news. You must read all this and think for yourself whether it really is dangerous. Okay, but anyway, let's think about this. If it's not an out of bounds read, if it's out of bounds right, is RCE possible? I also think it's quite unlikely, because the Photoshop, it probably will have ASLR and this pi enabled. Then you need to have an out of bounds read first to leak some pointers to bypass it. But the exploit is just an MP4 file. So when the Photoshop loads the MP4 file, the out of bounds read will likely make it crash already. Then you can't use the leak addresses for the out of bounds. And also, normally for this kind of file parsing exploit, you have to send the malicious file to the victim and then let the victim open the file to 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 run the exploit. So if the victim run one file that does out of bounds read, the Photoshop will just crash, and then you can't really do anything as a remote attacker. So to elaborate more, you might say that out of bounds write, it can work if there's no ASLR or pi because if there's no randomization of all the addresses, then maybe you can do rob or overwrite something on the heap. Or if this NX is disabled, then you might also write shellcode. So if you do pwn in CTF, then you'll know that without all these things, exploit is quite possible. But I don't think we should expect Photoshop to remove all this mitigation now. So likely it is not exploitable. Okay, so again, let's talk about how they managed to find the bug. I believe it's through fuzzing because it will take a lot of effort to reverse engineer the Photoshop program. So, and as you can see, the reports here is like it's like farming on. Got a lot. No way the person can find so much in such a short time. It's more likely to be through fuzzing. And actually, there are people that have written blog posts about fuzzing the Adobe products. Okay, now we look at this other bug in the Sonos speaker, which is reported by Synactive. Okay, you can check out their slides. The content here is just some part of their slides that I've copied out. So we look at this code. You see this decode frame. It will try to decode some part of the file. Oh, I forgot to say. So the vulnerability is with the ALAC file format. So if you go and search, is Apple lossless audio codec. And this one was from 19 years ago. So again, another legacy file format that probably none of us will ever use. So the flow is like this. This function, it calls decode frame. Then this decode frame is GPL code. It is code taken from some library, I think FFmpeg. So they take from FFmpeg, and because it's from FFmpeg, then they just read the Synactive guys. They just look at the FFmpeg source code. So this one is the source code, and this one is from IDA. So you see, the decoder will take this buffer from the stack and pass it into here as the output buffer. And then you see that this decode frame, it reads this number of bits from the ALAC file into audio bits. And then you store it into here. This one is something on a heap. So there's actually heap overflow because there's no bounce check. It just keeps reading. And then after that, it takes the whatever you copy into here, it loops through them again. So number of output samples. So this one, the number of output samples, as I said, it's not bounded. There's no bounce check. So they just read 32 bits from the file, which is the number of samples, and then they didn't check if it is too big or too small. Because they didn't check if the output buffer or all this buffer can fit. So maybe you can read 1 million output samples. Then this one will be too small. So after you read 1 million output sample, you can overflow this buffer, which is stored on the heap. And then after that, you also copy into here and also overflow this output buffer, which is this stack buffer. So overflow in both the heap and the stack. So quite nice. The exploitation on the Sonos speaker, there's no stack canary or no pi on. It's very weird. All these embedded devices, they always forget to enable stack canary and pi for their binaries. So once you have a stack buffer overflow, you can overflow and do ROP already, or just overwrite the return address to wherever. But there are also some problems. It is nice to exploit the stack overflow because you can do ROP and there's no stack canary and no pi. But you also, with the code over here, you will also overwrite the heap, overflow the heap. And actually it's not so good because it turns out that if you corrupt other chunks on the heap because of the overflow, the process will crash. Then if because they are freed before the function returns, that means that the crash will happen before the function returns. But your ROP, if you overflow the stack, the ROP will only work after return. So we must make sure that the heap chunks, they are not corrupted, or if not, you will not even reach the point where the ROP exploit works. This one is just a bit of troublesome things when you write the exploit, because you'll copy out by 2 or 3 bytes at one time. So this one is a visualization of this one. You see, in the stack, it's just this output buffer that we saw just now. Then if you overflow, you can just overflow the return address. So this one, LR, is on ARM, it stands for link register. So it overflow this one, and then you can do ROP. It's same as the return address pointer on Intel CPU. And then on the heap, we also have this thing that got overflowed. Then if you overwrite this metadata, and then when this function tries to free it later, the program will crash. Then you will never reach the ROP part because it will not return, and it will not return properly already. Okay, anyway, it was exploitable and they got a lot of money from this one. No stack canary and no pi, just do basic ROP like in CTF, and you get money to buy a lot of food. Okay. About how they find the bug is, as they shared in the slides, or they do manual review. They just read the code and they found out that there's a bug here. Oh, there's one thing I forgot to put in the slides, which is this one, which I think is quite interesting. So after this part, they talk about the patch. Okay, so they say many implementation have the same bug because they are all taken from the same open source project. So all of them have the same bug. But Apple's reference code also have the bug. So they say, oh, maybe the developers, they copy from Apple's reference code. And then that's why all of them have the bug. Then how come the Apple's own implementation don't have the bug? So this one is quite interesting. Maybe they fix it in their own implementation, but then they didn't update the reference code. Okay, moving on. This one will be quite complicated, but I think it's quite interesting. So this one is the Windows CLFS common log file system, where there's an out of bounds write, and you can use it to get elevation of privileges, or in Linux is LPE, to elevate from normal user to admin or system. So we will just quickly look at how this thing can be exploited. Not too much on the file format details because it's quite complicated. If you're interested, you can read these 2 links, but I think it will take you half a day to read. It's quite complicated. So this one, some background is the common log file system is a logging subsystem. It's seems like quite complicated one for logging, and they generate logs in this BLF format. So the bug is where they loaded, if you load a customized BLF file, means that you take a BLF file and then you modify some of the contents inside, and then you ask the CLFS driver to load it. Then you'll get an out of bounds write at an arbitrary offset. So let's see how this happens. So the flow is, You write a C program that first call create log file, and then it will create this file in the file system. Then after that, you modify the attacker can modify this file in the file system. So for example, modify the offsets or modify the sizes, like what we have seen just now. And then you call create log file again. But since this time the file exists in the file system, so this step is just to like get a template because you don't want to create the file yourself. That one might be too much effort. So just let it create and then modify some parts inside. And then this will load the file because it already exists, and then it will pass the file. And there's an out of bounds write already because you can the POC you can set some value for some offset, and then it ends up going through some code that overrides this field in a struct from this to this. And this one is it looks okay, but it causes more problems later, which we will see. So just take note that this value, it should be this, but because of the out of bounds write, is overwritten to this. Okay, then the exploit will call this function add log container, which as the name suggests, it do some allocations and write some values in memory. And then one of the functions it call is alloc symbol. So we look at the code here, which is taken from the write-up. So over here, V9 is this. So CV stands for count of bytes. So number of bytes in symbol zone. So as you can see, the pattern is always the same one. You read the number of bytes from the file, and then the byte, either this thing is not, there's no bounce checks being done, or the bounce check fails off. So let's see how it fails over here. The count bytes is being compared to check if it is greater than the signature offset. But and if it is greater than, just return with an error. But as we see just now, the bug has turned it from hex 50 to this very big number. So the result is, although the if statement, it wants to validate that this is not too big, this is already so big that you can put any value you want here for count byte symbol zone, and it will pass because it is checked if it's greater than this very big number. And if you say you put hex 1, 2, 3, 4, 5, 6, it will still be smaller than this. And then after the check passes, it is used to calculate this pointer v10, which is the object, then you plus the offset, this count byte symbol zone. And then use memset to write zeros into here. So actually until this point, it looks like okay, right? Because there is out of bounds, right? So v9 can be a very big value that make v10 point to outside of the object. And then over here, when we write zeros, we can write 0 into something that's outside of the object. So it's out of bounds, right? But it's just zeros. So the question is whether what kind of impact there is for this. So see, the example is like this. If you can corrupt a pointer in memory with this, because for example, if the pointer is a value like this, in little endian, if you want to write zeros somewhere like starting from here, then you can write zeros to these 2 bytes and onwards, and then the pointer is now this instead of this. So what it can do is to corrupt a pointer in memory to point to something somewhere else. Then when you move forward and call these 2 functions to do cleanup, it will try to call the destructor or some cleanup function. So you dereference this pointer, which is, so you purposely will choose an offset to corrupt a pointer that you want to use over here that is being used by the cleanup process. So you purposely choose an offset for v9 so that you overwrite and corrupt the pointer that is being used by close handler. And then close handler will read this pointer, and then it will find the VF table inside of it and call it. So for those not familiar with C++, uh, so when they do object-oriented programming, they will have this thing called virtual function call. And what they do is, in the memory itself, they store a table of function pointers. Then it will read out the function pointer from the memory location and then call that function. So at first, if the pointer is this, then inside here, there will be a VF table, virtual function table, that contains the function pointer to the cleanup function. So you read out the cleanup function's address from here, and then you run it. So all seems okay. But after the corruption, instead it tries to read the address to a function from here, which is not the correct place already. And we can do some exploit techniques, which is written in detail here. But to summarize is we do a heap spray. So a heap spray is, okay, if your memory is like this and the heap is here, then you allocate many things that you know the structure of in the heap. Allocate many here. And then let's say originally the pointer just now, maybe it's pointing to somewhere here. But after you corrupt it, the top few bytes are changed to 0. So maybe now it points to here. So if when the cleanup process try to read a function pointer, it was supposedly going to read from here, a function pointer. But now instead, it will read from here. And over here are the objects that you spread onto the heap. You control these objects. And then you must choose the objects so that you know the structure and you can write into the specific place some value where the cleanup function will read out and call as a function. So by doing so, you can craft a fake virtual function table in your heap spray area and then convert it into a arbitrary write primitive. So you start to call a function that lets you write to wherever you want. How I clear this? Okay, then once you have an arbitrary write primitive, you can override this privileges field in this token structure in the kernel. So in the kernel, for each process, there's this token structure. Then you can change the privileges field to change your privilege from normal user to admin or system. Okay, so this one is more complicated. So it's just to show how file parsing bug can also give you elevation of privileges on Windows kernel. So not sure how they found the bug, but they say it was found in the wild. Means that maybe some APT they exploit it, and then the SOC teams they found the exploit, the threat intel teams. And although we don't know how they found it, but there have been some conference talks on fuzzing CLFS, so you can check them out if you are interested. So the question is, if people without the source code can fuzz this driver to find bugs, then how come Microsoft with the source code didn't manage to do so? So, okay, now this one is the last bug that we will look at, which is quite popular. I think maybe all of us know about this because last year is a very big thing. This lib webp out of bounds write that can give you RCE. So I didn't have time to make slides for this, so we can look at the write-ups. Okay, so quickly going through, it is this bug. It was detected by Citizen Lab. So Citizen Lab, if you all know, they always find they are this human rights group. I think it's part of the Amnesty Human Rights Organization, and they found it this exploit part of the Pegasus spyware. So maybe someone died because of this exploit. We don't know. Anyway, the exploit, they say it's zero click because it exploited iMessage. And the component is in the image parsing framework. So maybe it happened something like they send this crafted image file through iMessage, and they managed to exploit iMessage to get RC on the iPhone. So this bug is quite dangerous. And the bug is for this libwebp. So let's look at the patch for this bug, because it is on libwebp, which is used by many different products, so including Google Chrome or Safari and Android and many others. So we take a look at how Chrome fixed the bug. So if we go here, we can click on this div, and you can see seems like a lot of changes are made, so it might be quite complicated. So we won't go through the file format because this one is really quite complicated. It is a mistake in the Huffman, in the part where they process a Huffman table. So if you know what is a Huffman table, then you might know what's going on here. But we'll skip through most of the details. It's just that just need to know, just want to share that in the WebP, they create this Huffman table to do compression. I think, yeah, compression. And then it is a tree structure. So if you make a specific tree structure, it seems like you'll trigger a code path in the parser that leads to out of bounds write. So if you're interested, you can read the blog post and find out more about this. But now we also want to think about the discovery. So how come the fuzzer didn't find this? Because actually Google's, they have this open source fuzz. They fuzz many different projects. And if you see here, they have this coverage report that show how much is being fuzzed. And according to the writer, actually this lossless, which is the component for that contains the Huffman processing, it is fast quite a lot of 97% coverage. So it's not that the fuzzer is not doing well also. But the problem is that the format is so complex that you need to craft a very, very specific Huffman table to reach the vulnerable code path. And if you make any small difference, the decoder will just give an error. So this shows that fuzzing is quite effective because you can try many different outputs, but many different inputs. But if you have a very, very specific situation like this, then you will miss out. Okay, then we just look at the summary. They say that Apple and Chrome, they responded to this quite well. They fixed very fast in just number of days. So that's quite good. Then the bad news is apparently when writing this, Android is still affected. Likely not confirmed, because they didn't release any advisory. And if the bug affects the Android kernel, then it will also affect Signal or WhatsApp or all these different programs. So this is just for some context, how this supply chain is a supply chain issue. So although the upstream libwebp is fixed, but all the fixes have to go down to the downstream also, to AOSP and then into Android and then into Samsung or Xiaomi, all that. Okay, then want to show you all this one, how it's exploited. Because just now we see that it is an out of bounds right in the Huffman table. But how can it be exploited? So in the case of Google Chrome, you can do you can write some JavaScript to load this WebP file, this crafted WebP file, and then I just quickly go through. What the exploitation process will usually include trying to find an object that you want to corrupt with your out of bounds. So a nice thing is you can change length for, and then if you change the length of some array buffer, internal fields, then you can use the array buffer to write to anywhere you want. So that is a nice scenario, but might be harder to get because all this blah blah we skip through. So it turns out that the one way to exploit this is override this reference count field in CSS variable data. So if you are familiar with use after free bugs, you will know that if you override, if the reference count is wrong, then there will be use after free because there is reference to the object, but it is free because the reference counting is done wrongly. If you don't know, also never mind. So just know that you can convert out of bounds right to use after free. Then if you have use after free, then you can do things like fast bin attack. Basically, allocate many objects, and then one of them you control the contents on, and then override the function pointers inside and get arbitrary code execution. So this one I won't go into too much detail because you need to understand a lot of Google Chrome internals. And if you are interested to learn, you can check this POC. 200 lines of JavaScript, so read at your own time. Okay, we are almost reaching the end. So this one again is a case is opposite from the previous two examples. It is likely not detected through fuzzing because of the complexity, and most likely through manual review and a strong understanding of this Huffman table. So I don't know, maybe you can say in CTF, if you like miss challenges, you understand all these things very well, it is helpful also. Yeah, so that's all. Let me summarize. So here we see file parsing bugs in many different kinds of software. We saw it in the Windows drivers, and also in Google Chrome, and also in embedded devices, and also in Apple's font parsing. So many different ways, many different places can have file parsing bugs. But as we saw also, not all are exploitable. It depends on the context. So I think one lesson we learn here is don't panic when you see CVE with high CVSS, or sometimes there'll be news article that say severe 7.8 bug or high severity bug. But actually, maybe they just categorize wrongly. So you can read the description more to really think about whether it really is dangerous. And then kernel and browser, because they let user write program. So for example, the exploit here, you can do so many things. You can, after you exploit the out of bounds, then you can allocate CSS variable data to get use after free. Then after use after free, you can allocate all this slot span object. So you can do many things to manipulate the heap contents and do heap spraying, all that things. So, and then calculate function addresses to corrupt the V table, all these things. So in the context of kernel and browser, it is a very nice place for people to exploit. As compared to like Adobe Photoshop, where you just double click the file and open it. That one, once the program crashed, then you cannot do anything anymore. There's no logic that you can do inside. And the last point I want to share is file parsing is really quite good. Many people like to do it. because you don't need to reverse. You just maybe reverse a bit, reverse the format a bit to write a parser that doesn't just parse parts that are not important. But then after that, you can just leave the fuzzer running, and then uh, after a few days, maybe you find some crashes. You don't need to spend too much effort reversing. But maybe your fuzzer, like the libpep example, manual code review is useful also in case the fuzzer may not detect the bugs. And one point I want to say is this Microsoft, I really don't know why people can fuzz their things for so many years. Okay, but this video will be on YouTube, so I hope they don't hear this. Okay, anyway, I think one day I can share more about fuzzing, different tools and different techniques. Okay, that's all. So as mentioned at the start, this one is the first of our bi-weekly sharing session. We'll do it every second Tuesday at 9 p.m. So we might find other speakers. For example, next week might be someone else. And for me, if I'm sharing, I will alternate between basic and advanced content. So for example, today is more advanced. Then maybe some other times I will share more basic stuff. Because I'm not very sure if everyone here how much you know. For example, for the kernel or browser exploit, that one is quite advanced. Which I myself also not very good at it. I just read about them, then try to summarize. Actually, I'm not expert at those things also. And to get some updates, you can follow our Twitter account for the registration form for the next session. Okay, never mind. Okay, any question? If no question, then the sharing is over. Okay, hope you all learn a lot. I realize some parts or most parts I didn't present very smoothly, so hope you all can follow.